All right, it's going to be science light, but we are going to dig in a little bit more to the nuts and bolts of the thermal side, the acoustic side, moisture, some of the things that we use insulation for and kind of how it does that, and also talk a little bit about how we test some of this stuff, because sometimes that also can give us, a little more flavor and context around that. So first, a lot of the things that we do, a lot of the tests we do are governed by ASTM, by standard test methods, and that really helps define, a lot of our material properties. This is kind of how we, I don't want to say get regulated, it's kind of how the industry regulates itself. So first off, thermal, So here we're going to jump into the science side of things. There are three ways that heat moves. Hopefully we've heard of these before, There's radiation, like the flame, the sun, a campfire, The reason we feel warm when we're out camping and we're standing by the fire, We're getting radiation from the fire. The reason our butt feels cold facing away from the fire is because space is cold, Bottom line. So we radiate energy all the time. Conduction, that's an easy one, We grab the handle of a hot skillet, it's hot, that's conduction, we feel it. And then of course convection, this is using some sort of a fluid, A boiling pot is like the great example of convection, The water gets hot, the hot water is less dense, it rolls up to the top, We get this kind of circulation going on. And so, we want insulation to slow down and or stop all of these modes, Because all of these things are always happening at the same time in our insulation. The big, the most common values that we talk about, There's K values that we publish for insulation, That's that's how easy it is, for heat to flow, Thermal conductivity is K value. So a low K value means better insulation, and then R value is kind of the other way to think of it, It's the resistance. It's how hard it is for heat to flow through a material. And of course, that's the one that's more intuitive, A bigger number is better insulation. But R value is really defined at a certain thickness, even though we do sometimes hear things like R per inch, as a way to kind of pull thickness out of the conversation. So again, a good conductor has a high K value. Good insulation has a low K value. R value is just the opposite of that. And in terms of materials, just some common materials from really good conductors like steel. Even you see glass, solid glass, it's actually a pretty good conductor of heat. But fiberglass, K value, much, much lower than that, and we'll talk about the why. So first off, this is a photo of one of the instruments that we use to test insulation. Now you can see this is a pretty big, thick, chunky piece of insulation. This is some building insulation, what you would put into like a ceiling or a roof. But we use the exact same instrument even if it's 1 inch thick ductboard. Now, typically, when we run this test, you can see on that first bullet, we have what's called our 75 degrees is our mean temperature, our average temperature. So we have a cold plate that's at 50 and a hot plate that's at 100, So the middle temperature is 75. And we are basically just measuring, how much heat flows through here. We keep these plates at their temperature and we figure out how much power does it take to keep the hot side hot. That's it. It's pretty simple. Now there's kind of a lot that goes in to make sure you don't have heat flowing sideways and things like that. And that's sometimes really where the science comes in. But the test itself, it's pretty simple. And how much heat flows varies with temperature, So if we were testing this at 200 degrees mean, it would do differently than at 75. So that's one of the reasons that just as an industry, we pretty much pick 75 for most things, though, if we're doing a commercial job or something, the spec might call out something different depending on the application, If we're insulating, a steam pipe, that's running at 400 degrees, well, we don't really care what it does at 75, So that's why we oftentimes, get these other requirements. And these last three bullets wanted to kind of break this down for us a little bit. So if we had no insulation in this instrument at all, and we just had our hot and our cold plate, the breakdown of how the heat flows would be about 63%, about 2/3 of it would just be radiation. So convection, right, we'd end up having little air circulation loops in here if there was no insulation. That'd be about 1/4 of it. And conduction just through the air itself would be about 11%. So what insulation does is it changes this mix, right? It shuts down convection entirely, right? All the little fibers make it so that that air can't really move very well. Of course, you can't see through insulation, so it actually does shut down quite a bit of insulation, and then we're left with some conduction. It does this. We still have heat being conducted along all those little bitty fibers, right? But they are, you know, 1/10 the size of a human hair. They are tiny. So even though glass does conduct heat pretty well, right? It's such a skinny little fiber, it doesn't. We get this little light blue arrow, so heat being just conducted through the air itself, and then the little red squigglies, right? We've got these fibers, they're also radiating to their neighbor. So we get radiation kind of bouncing its way through the material. But this is how insulation ends up working once we put it in the way of things. And this really, these functions are all still there, but because we have the insulation in place, it slows things down quite a bit. So by how much? The very top one, right, some sort of fiber. And so when I say fibers and we show R from anywhere from R2 to R4.7 per inch, that really covers a broad range. R2 per inch, right, that would be something that's got a really coarse fiber. Not so much in HVAC, but maybe things like cellulose, right, and to go into a house, right, that could be as low as R2. Cotton shoddy might be a good example of something that's a really, really coarse fiber, so it's not gonna have as much of a performance, right, and then up to R4.7 per inch, or even up to closer to R5 per inch, that would be something with really fine fibers. That would be, again, not so much HVAC product, but like our aerospace fiberglass, which has got a super fine fiber, and that ends up being more like closer to R5 per inch. And we're gonna hit on this again in a minute, but R5 per inch is pretty much the limit of anything that has air, that uses air still in it, right? So if we want better than R5 per inch, one of the things we do is we swap out the air, right? As TJ was saying, in polyiso foam, we get rid of the air and we put in pentane, right? Pentane has got a lower thermal conductivity than air does, and so we get better performance. Same thing goes with like spray polyurethane foams, right? We use a blowing agent, some sort of refrigerant, that has a lower thermal conductivity than air does. That's how we get this up to R8 per inch in closed cell foam materials. Yes?
Yeah, would that be used more in the commercial application?
It could be, doesn't have to just be commercial, right? I mean, we see, you know, foams in residential products a lot. Again, not so much HVAC, but like building insulation, right? Especially, we see spray foams in those plenty, but they do also get used in commercial applications too, right? Then you end up kind of balancing what you need from a thermal perspective against, I don't know, fire performance or other things, right? Lots of those other factors come into play. Good question. If we want to go beyond that, we kind of need to do something different. Aerogels, right, up to R10 per inch. What do we do there? Well, there we're using air again, but then our spaces between the particles is so small that it's kind of like we've broken the air. Like air can't transfer heat the way it does normally by conduction because we've made these spaces so short that we interfere with how just the air can conduct heat. That's why aerogels get R10 per inch, and then something like vacuum panels up to R30 per inch. Well, again, there we've literally gotten rid of the air. It is just a vacuum, so the only thing left really is radiation, and we can control that with shiny surfaces pretty well, right? So that's kind of why some of these materials get some crazy levels of performance, but right there, I don't know if anybody's ever tried to price this stuff out. It's expensive. It's really, really expensive. You know, you kind of argue that it might be cheaper to just wrap it in a few layers of $100 bills and you might get about the same performance. Right, and of course also things like vacuum panels and aerogels, they tend to be pretty fragile, right? If a vacuum panel loses its vacuum, guess what? It's not getting that performance at all. Aerogels, likewise, awesome performing material, oftentimes very hard to handle, very unpleasant to handle if anybody's ever done that. They're very dusty and yucky. But just to give you a feel, one thing I do want to spend a couple of slides on is what about just reflective? We've all seen ads and data sheets and marketing pieces or heard some sales guy try to tell us something that seems too good to be true. Reflective insulations, really using this shiny foil layer to deal with radiation. There has to be an airspace next to that shiny surface. If I just take a piece of foil and I just put it flat here against the wall, it's not doing anything anymore, right? It's got to be off of that, whatever I'm trying to insulate, it's got to be separated from that to do anything at all. Which direction the heat flows actually does make a big difference. So the little table here at the bottom, this is right out of the ASHRAE handbook. ASHRAE has done a great job of cataloging this sort of information all together, and this is just a little snippet of what's in the handbook. So depending on the thickness of the airspace and the direction of the heat flow, right, we can get, and this is just kind of two surfaces, two shiny surfaces looking at each other, right? What's the R value of that one single airspace, right? We get anywhere from as low as R1.8 to as high as R5.6, depending on the direction of the heat flow. And actually, it also varies just by temperature again. And that's because of this. If we look at a piece of bubble wrap, right, what's going on in here? We've got radiation coming in. It's shiny, so we've got quite a bit of radiation reflected back. But then within the bubble wrap itself, right, so then we've got radiation coming off the backside of the foil and also getting reflected back. Remember, these bubbles still have air in them, right? So there's still conduction through the air. That still happens. And it's full of air. We can get little tiny convective loops. So heat will still transfer through this thing. And again, in this piece means that for this foil to work, there's got to be an airspace here. So all of these things mean, and the important piece here that I want you to remember is, right, again, we still have air in here. So that means 5 per inch is about the best we could do, right? In the ASHRAE table, it was 1.5 inches airspace that gave us an R of 5.6. What makes my head explode is when the folks that sell this try to tell you that you can get R19 out of some little bit of bubble wrap. It is physically impossible, right? All of the physics says, no, you can't, right? If you had no air at all in there, which by the way would make the bubbles collapse down, right? You might be able to get close to that because it would start to look more like a vacuum panel. But you know, a lot of the things, if you were to dig into the test reports for some of this stuff, right, they've done weird things like they've got some big fat spacer, right, to take the bubble wrap and space it off of the duct surface. And then they're also trying to count some outer airspace that's really exposed to the room and not kind of sealed off. So I wanted to add this in this time around because this is one of these things that I get questions on a lot. You guys might get questions on a lot. And sometimes this seems sexy and far less expensive and et cetera, right? And I will tell you, it can work for a little bit of R value, but it does not, it just cannot deliver some of the claims. Before I move on to moisture, how are we doing? Yeah? Yeah.
You may have already covered this, but so I noticed like when I'm looking at ductwork of a certain thickness, let's say 1 inch, versus flex insulation at the same thickness.
Yep.
The R values are different.
Yep.
Why is that?
So excellent question, and I guess I may have kind of glossed over it. So one of the things that drives R value, like at the same thickness, would be density, right? So the more fibers that we can pack into a given volume, the better then those things help scatter radiation, basically, is what it's helping to do more. Instead of that 2/3 radiation, 1/4 convection, 10% conduction, when we put insulation in the way, it becomes like 75% conduction through just the air and 25% radiation and no more convection. So we've changed the mix. And so by packing in more fibers, that's how we get more R value, because we're blocking more radiation now. Great question. Yes?
So that would explain why some states require a R value of 8 opposed to when it comes to inspecting.
So a lot of that ends up being driven just by your climate, right? So it should be mainly by your climate. It also ends up being driven in different states by what version of the code they've adopted. But underlying all of the energy codes anyway is just what's my climate, right? So the colder my climate in general, right? Because heat, even in what we would consider a cooling dominated climate, heating ends up being one of the biggest costs. So they drive a lot of it from that. And so, yeah, the colder my climate, the more R value I'm gonna need to then manage heat loss through that ductwork. Yep. All right, moisture works kind of the same way, right? I mean, heat goes from hot to cold. Moisture, similarly, humidity moves from high vapor pressure to low, and this applies anywhere. Commercial office space, which is typically, right, we're trying to say it's 72, 50%. The tropics, frozen tundra, right, there's quite a range in what that water vapor pressure is. And to help manage that, we use vapor retarders, right? And all that is gonna be a material that slows that down, right? Just like insulation slows down the transfer of heat, a vapor retarder slows down that transfer of water vapor, right? Water vapor, kind of like heat, it's kind of like this percolation sort of process. It's a pretty slow, bubbling in its way through sort of process, and a vapor retarder helps slow that down. Now, when it's something that's like foil faced, right, it kind of more like stops it, right? If it's something that's not foil faced, then it's more of a throttle. And again, for something to be considered a vapor retarder, it's usually got to have a PERM rating. And I think my next slide talks about, what a PERM is, right? The PERM rating has to be 1 or less for the building code to consider something to be a vapor retarder. And again, PERMs in the US, it's all, of course, it's, we use imperial units. They're all kind of wonky and weird, right? It's 1 grain of water, which is 1/7,000th of a pound, right? Going through a square foot of material in an hour, and a PERM then would be under a driving force per inch of water vapor pressure. I think we've all heard the term PERMs before. Again, we just need to know that it's, less than 1 means something is considered a vapor retarder. Greater than 1, it's kind of really not. And most, anything with a foil on it is typically going to have a PERM rating of like 0.04 or less, right? So very low. All right, some examples of materials and what their PERM ratings are, right? Gypsum board, 50 PERMs, latex paint, might be 6 if it's just 1 coat. Polystyrenes, 1.2. Craft paper, right? If anybody's ever seen like a craft-faced bat, that's about 1 PERM. That's kind of right there. That is considered a vapor retarder, just. Right, and then of course we get to things like polyfilms, get to be, 0.8. Foils can even be down to 0.2, right? Vapor barriers would be kind of in this class of material, right? Vapor retarders, more kind of in that middle class of material. If we think about we're wanting to keep water vapor from moving from where it is in the air to some cold surface, right? That's why we use them. And we want to make sure that we don't get condensation forming on whatever our cold thing is. For us in HVAC, it's probably an air-conditioned duct, right? So that ductwork is carrying 55-degree air off the coil. That metal is cold, right? We don't want it to start sweating. So right, we're going to put our vapor retarder outboard, right, outboard of the insulation, so that this surface that the water vapor sees is warmer than our cold ductwork. If we flip it around, like on the other side, that would be backwards. This is going to sweat, and then our insulation is going to get wet, and wet insulation isn't really good for anybody. Can you double it up? Does doubling it up help? In general, no. We don't really need 2 vapor retarders. If we're going to use one, we really just need to use the one and then make sure it's in the right spot. Like, that becomes the important piece here. Using 2 ends up more often than not, having 2 vapor retarders just kind of ends up with spots for moisture to build up that we don't want it to, right? And that ends up being no good, especially if we've got something in between them, right, like fiberglass, where we could actually accumulate moisture, right? I will tell you, you might look at something like this and think, well, what about Expect polyiso foam? It's got foil facers on both sides. Isn't that a double vapor retarder? It's not, because that's a solid material, right? We're not gonna get moisture building up inside there, because moisture won't go through any of that material. It's more like if we, had foil facer, fiberglass, foil facer, like that sort of a combination is what we would not want. We've covered heat and moisture. Acoustics. Why do we control noise, right? Why do we use insulation for acoustics? All kinds of good reasons. Right, acoustics is one of those things that impacts a lot of our life, right? So the quality of workspace, productivity, our ability to communicate, your ability to hear me in this room is dictated, right, kind of in part by the acoustics of the space. And then we get into, things like worker health and safety, recording studios, lots of reasons why we might want to control noise, right? So the basic noise control strategy is always, hey, if we can, let's quiet it at the source. The more that the mechanical engineer can spec a blower in a system with less noise, that's a better thing, right? We're creating less noise at the beginning. Where we all come into play is that oftentimes that's not really enough, right? So we're gonna try to quiet noise along the path. That's what our HVAC products are doing from an acoustic standpoint, right? Noise is created here. Over here, there's somebody that doesn't want to hear it, and we get to intercede somewhere along the way, hopefully, right? If we fail as an industry in both of these two, and we start handing out hearing protection, especially if it's to some person sitting in an office, then for God's sake, we've failed utterly. When we hand out Hearing Pro at the end, that's when we haven't been able to be successful elsewhere. Sound has got a lot of factors to it. There's volume, there's frequency. We measure sound volume in what we call decibels. Decibels is, not even really a proper unit. It's really just a label. It's based on a ratio of pressures, which is why we call it sound pressure level. Sound pressure level in decibels is how we describe volume. 0 decibels would in theory be like the threshold of human hearing. All of us in this room, we can't hear 0 anymore. Like infants can hear 0 decibels, or just barely. Like, we've all abused our hearing through our youths to the point that that's not where we are anymore. But, right, so that's why it ends up being more like 10 or even above. Most voices, regular conversation ends up being in this 50, 60 range. And then we get at the loud end, back row of a concert, lawnmower, it's a gas lawnmower, right? That's also around 100. Passenger jet at 120, right? 120 is also considered the threshold of pain. Don't expose yourself to this if you can help it, please. Right, OSHA would say, right, if we're gonna be exposed to more than 85 decibels on an 8-hour basis, right, we should be wearing hearing protection. So again, that kind of gives you a good sense of what's a safe range. The other piece that's important to think about is how we perceive changes in decibels, because again, this is where we come in. If a sound ultimately will only be changed, think reduced, right, by 0 to 2 decibels, we're not going to notice that, right? We're not going to hear that change. 3 to 4 becomes kind of right where we'll start to notice, oh yeah, that's louder, quieter, right? 5 to 8, clearly different. 9 to 10 ends up being how most people would perceive something as being twice as loud or half as loud. And this is important because if we are then investing money in materials, right, to quiet noise down or quiet a sound down, right, if it's going to cost us a whole bunch of money and effort and all we're going to get is a couple of decibels, you kind of, right, got to step back and be like, is that really the right choice, right? But if we can invest some time in materials and we get a clear difference, well, then that becomes probably worthwhile, right? So this kind of change is good from that, to understand a sense of that is good for that reason. Sound comes in frequencies, different pitch, and we'll see on the next slide like where different pieces of equipment fall within that. But we've got anything from 250 hertz and below, the rumbles, mid-frequency, which is like speech, 250 to 4,000 hertz, and then above that is the hisses, typically produced by airflow and pieces of equipment. 20 hertz tends to be the bottom end of what we can hear. And actually, once we get down to 20 hertz, you kind of more feel it than hear it. And then 20,000 hertz is at the upper end, kind of, again, of most human hearing. But most of our experience in day-to-day life is not in that range. It's more in this 60 to 5,000 sort of range, right? But we can see where speech falls in right into the middle of this, and then different types of pieces of equipment, what sort of noise that they tend to produce in terms of frequency range. We do a bunch of testing on our materials. We do a lot of this testing. Actually, there's even another one here that we didn't list that I'll talk about in a minute. That we do all of these at JMTC, at our labs. The photos are of our couple of chambers. This is a shot of the wall of our hemianechoic chamber. I'll talk about these a little bit more in a minute, but sound transmission loss and absorption end up being some of the bigger scale tests that we do. And then the tests down here at the bottom are more how to just characterize the material itself. In sound transmission, things that are important, this would be reducing sound as it goes from one space to another, going through walls, floors, roofs, and really the whole system ends up being driving how things perform. Transmission loss is how we characterize how well we knock noise down as it goes from one space to another. Sound transmission class, STC rating, this is kind of the single number rating that we use in the industry to describe how well an assembly performs. Again, we've got some ducts shown, but this tends to be, STC, it tends to be more applied, right, to like walls, right? Walls, ceilings, doors, that sort of thing. Sound absorption is really, just what it sounds like. As noise hits a given surface or a given material, how much of it is reflected back into the room, how much of it is absorbed into the material itself and just kind of dissipated as heat, basically. Sound absorption coefficient is how we characterize that performance. And then noise reduction coefficient, or NRC rating, again, this is that single number rating that we, where we basically take several absorption coefficients and average them together to give a single number as a quick and dirty way, right, to compare different materials. What makes a good absorber? Fiber diameter is one. The smaller the fiber diameter, the better. We want more fibers in the way, in that material, so that as that sound waves pass through, right, it rubs against the fibers and it loses energy that way. So the more fibers there are, right, the better that material will perform. So if I've got one big chunky fiber, right, that's not going to do nearly as well. If I can take that and split it up into 10, right, that's going to perform much better. Density, similar to thermal, in that unit of volume, right, the more fibers that I can put in the way, the better of an absorber that material will be. And then thickness, it's one of those easy ones, right, kind of just like R value. More material, thicker material is going to absorb sound better, just like it's also going to give you a higher R value. And then mounting method ends up being that last one. If we put like an airspace behind our material, and again in HVAC, we don't do that very much, right? But if you think about like this ceiling tile, because it's got a plenum space above it, it performs better as an absorber than if I were to take that same material and just stick it like this, like just stick it to the wall. And how do we run that test? We use what's called a reverberation chamber. There's a little photo of JM's reverberation chamber with some schwanky lighting in it. We don't normally run a test with a pretty pink light, but basically though, we use this chamber, and it is a very echoey chamber, right? It is all concrete surfaces, and then we've got these various vanes and diffusers to help bounce the sound around through the course of the test. And we will turn the noise on, and then we turn it off, and we listen to the echoes. We basically measure how long does it take that echo to fade away. When the room is empty, in our chamber at least, it's like 3 to 5 seconds that it takes that echo to fade away, because it's a very reverberant space. And then we run that measurement again, right, with whatever the material is, right? So as the echo fades away, it looks like this, right? We've got our noise on, we turn it off, the sound echo decays away, and then this is our background level, right? And we measure that slope. And then we do it again with the material in. And when the material gets in, the slope gets steeper, right? By comparing the difference, we can calculate how much sound is absorbed by the material. So I don't know, I've been doing this for a while. It seems pretty straightforward to me, but that's just to give you a sense, right? We're just comparing echoes. That's what ends up giving us. First, we calculate a sound absorption coefficient, which ranges from 0 to 1, and then through 250, 500 hertz, 1,000 hertz, and 2,000 hertz, those four we average together to get the noise reduction coefficient, or NRC, which is what you see on all of our data sheets. An NRC of 0.7 truly means that about 70% of the sound that hits that material is absorbed versus reflected back. 250 to 2,000 hertz, again, speech range, right? That tends to be the ranges that we care the most about. 0 to 1, more or less, ends up being the range that we get for that sort of material. One thing that I did want to touch on, because right in HVAC in particular, we publish for materials things like sound absorption, but at the end of the day, in the actual building, right, what really ends up mattering is what's called insertion loss. That's kind of what a mechanical engineer designing a system, this is what they're actually trying to get to, right? Because this tells us if I have 80 decibels coming out of my blower at one end, what comes out of that diffuser, right? So if I've got 80 dB at the blower, and I want to be sure that no more than 20 dB comes out of that diffuser, right? I need 60 decibels of insertion loss that I need to somehow find, right, through that duct run, right? Now, we get some of that just from elbows and branches, but the other thing that we get it from is by lining our ductwork, right? By having some insulation materials inside there. But that depends not only on the material, but on the duct, right? So this graph shows the exact same, and I think this is just some 1 inch, right? 1 inch thick fiberglass duct liner. Same product. The only thing that's different is the size of the ductwork. This really big number, right, there's 12 inch round, 24, 36, 42, 48 round. As the duct gets bigger, right, and more of that sound is going to be able to go down the ductwork, right? It's not interacting with the insulation as much. And so insertion loss is very much a system kind of metric, right? And now we've done some of these. There's not very many labs that do this sort of testing. We can do it at our lab, and there's a handful of other ones, right? But it obviously becomes much more complicated. I can verbally share with you, we haven't like published this or anything, but I can verbally share with you, if anybody has ever gone to the ASHRAE handbook, or if you have access to it, there's tables and tables of insertion loss data. It is all Johns Manville data, because we donated product to a big research project that we did a few years ago. And so every scrap of 1 inch and 2 inch rectangular and round and oval data in that industry book, it's just like a big data page for JM. So there you go. Like There's a freebie. But this ends up being the important piece, right? Even when a mechanical engineer is speccing, NRC of whatever for a product, it's because he's going back to insertion loss. Sound transmission loss, right, which we talked about as a way to rate walls and floors and other sorts of building assemblies, right? This is how much does a barrier reduce noise? Again, higher number is better, right? It's in sound transmission loss is in decibels, right? We're just saying it right, reduces by so many decibels. Things like mass and thickness end up really driving how well an assembly performs. Again, sound transmission class, that's the single number rating, and it is measured in decibels. Again, higher is better. It's kind of in the speech range, so it looks at usually 250 hertz to 2,000 ends up being kind of the range that it looks at things. And finally, last one on acoustics, what is active noise control? How does that compare, right, to materials, things like that, right? And active noise control is truly just that. It's where there's a couple of microphones, and they put a loudspeaker somewhere on that duct, and there's a computer controller, and it emits its own noise. It sends out a signal that literally cancels out the sound that comes down that ductwork. I will tell you, this works really well at really low frequencies, right? So the lower the frequency, the longer the wavelength of sound, and kind of the better it kind of stays put. It is well contained by the ductwork. The higher the frequency, the shorter the wavelength, the more likely that sound is to not just go straight down the ductwork, but to like take some angle and bounce off the duct walls and right, do the things that make it be controlled well by insulation. To me, active noise control and passive noise control like insulation work really well together because insulation does an awesome job at controlling noise that's in that mid to high frequency range, but the really low frequency rumbles are tough because those sound waves are so long. Active does awesome at the low frequency. So like, to me, this doesn't replace insulation. It is an excellent complement to insulation, especially if like there's a big need, right, for a lot of noise control across a broad range. All right, and finally, environmental properties of insulation. Insulation, when it comes to energy efficiency, when it comes to bigger picture stuff, reduced carbon emissions, you name it, right? Insulation is really the unsung hero because it's always done this stuff and doesn't always get the due that it's deserving of. But insulation is a very important piece of this. If anybody doesn't know, right, buildings globally, right, are responsible for about 40% of all the power that we use on the planet. They are a huge sector when it comes to energy consumption. And as the slide says, there is no quicker or cheaper way to reduce whether it's an energy footprint or a carbon footprint than with insulation. It allows equipment to operate more efficiently. Most fiberglass products contain some amount of recycled content, and it pays for itself in dollars or emissions, however you want to look at things, from minute one. So this ends up being a big deal, and again, more and more often, right, especially on commercial jobs, right, we get asked these questions, right? We get asked them, I'm sure you guys get asked them, right, whether somebody's pursuing lead points, or if there is some sort of, mandate in a given jurisdiction, right? It could be any number of those things. As a good example, how to offset the emissions from a truck. So that's 18,000 pounds of emitted CO2. You could do a few different things. You could swap out a little over 300 light bulbs from incandescent to LED. You could plant 360 trees, or this is a pretty hot steam pipe, but if you had some process steam in a building or a plant, right, if you just replaced 8 feet of that 4-inch pipe, put 2 inches of insulation on it, same sort of equivalent savings, right? So, as you can imagine, a bare pipe at 350 is dumping off gobs of heat to the surroundings, right? And so to contain that and to not mean that heat has to be made up for at the process, right, that's where those savings come in. But insulation does an enormous amount. And, now granted, right, HVAC systems don't usually run at that sort of a temperature, but right, if we think about the savings that we get by insulating our ductwork and our duct systems, right, it ends up being similar, especially when we think about, right, in a building, a commercial building where there's lots of it, right, it adds up pretty quickly. There are tools out there that we can use to help if we're tasked or asked to answer these sorts of questions. 3E Plus is a great tool. It is free. It is a piece of software. It is web-based now. I don't think you even have to download it anymore. It's put out by NEMA, which is the fiberglass and mineral wool kind of industry group. It can do things like heat loss and heat gain and surface temperature for worker safety, condensation, but it can also look at things like energy savings, and it can also look at carbon savings, right? It's able to connect those dots between energy to carbon, because of course that depends on how you're producing your energy. So that's an excellent tool out there if you ever have need. The folks on our tech services team, Heather and Tyler, are well-versed in this as well, so you can always reach out to them and they can help navigate some of that if need be. Environmental product declarations, EPDs. EPDs are basically at the manufacturing side where we kind of do an accounting of the environmental impact of a given product. And that includes everything from the raw materials that we source. It includes transporting those raw materials to our plants. It includes the energy and water that we use in our manufacturing processes. It also includes transportation beyond, right? It includes warehousing. It usually includes installation, or at least an estimate of that. It doesn't include use yet. And then it includes like landfilling, right? So a whole bunch of sections. We kind of collect that information all together, and that's what we publish when somebody asks, if an architect or a specifier asks for an EPD. We have that information for most of our fiberglass and mineral wool products have that sort of information, right? There's a big list of products here, and so that ends up being very important because, again, right, depending on the project or the jurisdiction, they might require that sort of information.